In today's lesson, we're going to look at some more complicated problems dealing with permutations and combinations. There's actually going to be a few examples where we need to use both permutations and combinations to solve a particular question. Otherwise, the problems are going to appear as though ones we've seen before, except they're just going to have additional complications where we're going to have to use a bit of a different problem solving approach to deal with. So let's jump down to this first example. It says, how many arrangements of the word poppies can be made under each of the following conditions? So A is like, we're just going to rearrange all those different letters with no restrictions. Now, the immediate thing to notice up here is that this is going to be, you see that word arrangements. So we're thinking of permutations immediately. It's like the order of the letters is important. We also have a repetition of the letter P, which occurs 3 times. Now, to solve a question like this, we can use this equation, which was discussed, I believe, back in lesson number 2 or 3, which is if you have permutations with repetitions, the number of different arrangements is equal to n factorial. So n factorial being the number of different elements you have. And then a factorial, b factorial, c factorial, that's the number of times that a specific element repeats. So if we go to part A here, the number of elements we have are just the number of letters within the word poppies. So that's going to be 7. And then only one of those elements repeats. So we're going to say A is there. Let's change this. It looks too much like an H. Okay, so that's going to be 3. And then for for P. And then we just plug it into the equation. So it would then be n factorial divided by a factorial, which would be 7 factorial divided by 3 factorial. And that's going to be equal to 840. Okay, so no problem. That's a problem we could have dealt with back in one of the previous lessons. Now, what becomes more complicated is if we have arrangements that have repetitions, and in addition to that, we start to actually place additional restrictions as well. So it says we still have this word poppies, but now it's placing the restriction that each arrangement has to start with the letter P. Now, the problem with this is, and I'm just going to kind of like point it up right here, or make a point of it up here. Previously, we would have used the fundamental counting principle to like solve a problem like this, but the fundamental counting principle is not helpful usually when you have repetitions. It's like really difficult to utilize. So I'm just going to make a quick note here where I'm going to say the fundamental counting principle is not useful for permutations with repetitions. Just like our part A. Part A, we didn't use the fundamental counting principle to solve that question. We used an equation established to deal with permutations with repetitions. But again, the issue now with B is that we're placing an additional restriction to this. So here's the logic I'm going to use in terms of how I'm going to solve this problem. So I'm going to say if the first letter must be a P, what I'm going to do is I'm going to remove a single P from the word poppies. And then find the number of arrangements for P on its own and the number of arrangements for the remaining letters on their own. So let's just pretend we take away the first P. So if I take away that first P, then the remaining phrase we'd have right there would be oppies. Okay, now I'm going to color code this just to show how I'm going to do the two separate calculations. So we're going to do the number of arrangements for P on its own. We've removed a single P. It's on its own now. And then we're going to find the number of arrangements for these remaining letters right here. Okay, so let's jump down and do this now. Now, if you've removed a single P and you find the number of ways that you can arrange a single P, well, there's one. You just have one spot in which you can actually put that P. So that would simply just be equal to 1. Now it's an end statement, so we're going to multiply. And then, now I have to find the number of arrangements for like the remaining elements here. So that's for like the phrase oppies. So now what we'd have right here is for this part, we would have 6 elements, so 6 letters. And we have a repetition of, it's no longer P repeating 3 times. And this portion right here, just P that's repeating twice. So we'd have A is equal to 2. And that's going to be for P. Okay, so if I calculate that, this would then be, okay, so that's 1 for the number of arrangements for that P I separated on its own. And then the number of arrangements for what these remaining elements are would be, you would have 6 factorial. So that's the number of ways you can arrange the letters O, P, P, I, E, S. And the 2 factorials is accounting for the fact that the P repeats twice. So if we calculate that, 1 multiplied by 6 factorial over 2 factorial, then this would just be equal to 360. Now C now places an additional restriction. So it says now the first 2 letters have to be P. So I'm going to do that same strategy again, where I'm going to separate the 2 different parts of, separate 2 of the P's from the rest of the word. So I'm going to separate like this. So we're going to take 2 P's on their own. Okay, because the first 2 letters have to be P's. And then I'm going to look at what's left over. Now, if we look at the word poppies and I remove like the first P and the second P, then the remaining word would just be O-P-I-E-S. Okay, so now I'll color code it again. Okay, so we have to figure out the number of arrangements for, I've taken away 2 P's, okay, and we have 2 spots to place them. And then after I've taken those 2 P's away, I then have these 5 letters, and we're going to find all the different ways we can arrange them. So what this would look like is for this one, what you have is you have 2 elements. So n is equal to 2. And there's a repetition of those elements. So that would be A is equal to 2. And then that's for P. Now for this remaining word, OPs, I guess, all we have right here is we just have n is equal to 5, but none of these letters repeat. So now when I go ahead and calculate this, what this would look like is this would be equal to, so for the number of arrangements for the 2 P's that have been separated, okay, that's going to be n factorial, which is 2 factorial, divided by a factorial, which is 2 factorial. So you have 2 factorial over 2 factorial. And then we're going to multiply by. And then if you have 5 elements, there's no repetition. The number of ways you can arrange them is just going to be n factorial. So that would just be times 5 factorial. So this is just going to be equal to 5 factorial. And 5 factorial would be equal to 120. Okay, now D, this gets a bit tougher now. So it says all of the p's have to be together. So there's a lot of different spots where like the 3 p's can be side by side. Now I'm going to do one scenario where I start them at the beginning. So I'm going to do this. I'll say consider the scenario where the 3 p's start the, I'll put in quotation marks, start the word off. I say word in quotation marks because depending on like where the placement of the letters are, the word can be total gibberish. Okay, so we're going to separate like this. Now, this is only one scenario, so we're going to have to look at the other scenarios in a moment. Okay, so what I'm going to do is I'm going to take all 3 of the p's and pull them out of the rest of that word from poppies. So we're going to separate P, P, and P. And I'm going to pull that away from the word poppies, which is just going to leave me with O, I, E, and then S. So we'll color code it. I'm going to find the number of different arrangements of, if you have 3 p's, you can put them in whatever order you want. So this would be n is equal to 3. Okay, because 3 places to put those different letters. And you have a repetition of 3, okay, because you have 3 p's there. Okay, and then the second part here. So then you have n is equal to 4, but you don't have any repetitions. So it's just going to be 4 factorial for the number of different arrangements. So if we calculate this now, this would then be, okay, the number of different arrangements for 3 p's would be 3 factorial over 3 factorial. Now, just note right here that's equal to 1, and that does make sense because it doesn't matter if you have like 3 placeholders to start off. It makes no difference like where you put the different p's. So, and because of the repetition, there really is only one arrangement you can actually have there. Okay, then we multiply by. Okay, if you have an arrangement of distinct elements and we're using all of them, it would just be 4 factorial. So we're just going to multiply by 4 factorial. So it'll be 1 times 4 factorial. And 1 times 4 factorial is going to be equal to 120. Now, that's not quite the correct answer yet because that's assuming that we're starting the word off with the 3 p's, at the start. So even though I'm not going to use the fundamental counting principle, I'll just do an illustration just to communicate like what I'm talking about right here. So fundamental counting principle, we typically just write down horizontal lines with the different elements you're going to place. So again, the word poppies has 7 letters in it. So we have 1, 2, 3, 4, 5, 6, 7. And the scenario I did is I said we're going to put all of the p's to start the word off. Now, they don't have to be at the start because it doesn't give that to me as a restriction. So this is one scenario where you have this group in this position right here. There's actually a few more scenarios as well. So we're just going to take this group and just keep shifting it over by 1 until I get to the end of the word. So this would be one scenario. Okay. Another scenario is you could start the p's right here. So that would be 2. Another scenario, you could start them right here. Okay, so that's the third way in which I could have the p's grouped together. Okay, here's scenario number 4. Let's make sure I'm just matching it up here. Okay, scenario number 4. And then scenario number 5 is just going to be, it's the p's are all directly at the end. So because there's 5 total scenarios in which the p's can be grouped together, we're just going to take that answer for the first part up here, which is 1 scenario, and then just multiply it by 5. So then this would be 120 multiplied by 5 would be equal to I don't think that's 120. This right here would be 4 times 3 times 2 times 1. This, I got ahead of myself. I was looking at what the final answer would be. Okay, 4 factorial, that's actually equal to 4 times 3 is 12, times 2 is 24. So this would be 24, and then we're taking 24, we're multiplying it by 5, and that gives me 120. Okay, good that I caught that mistake before it was too late. So that's 120. Okay, one more. This is probably as complicated as it gets for one of these questions. Okay, it says the first letter has to be a P, and then it says the next one is not a P. Okay, so again, because it tells me the first letter is going to be a P, I'm just going to take that and I'm going to remove it from the rest of the letters in the word poppies. So again, we'll separate. Okay, so we're going to separate P and so we're going to pull out a P, and that's going to leave me with O, P, P, I, E, S. Okay, so for this one up here, you just have one element. And so there's only, if you separate that a single P, the number of ways you can actually place it to start the word off would just be 1. Okay, so that's going to be 1. Now, this one right here, we have to break into 2 separate parts because there's just a restriction on what the second letter is. So we're going to clarify here. So we're going to say second letter. But by second letter, I mean the first letter in this group of elements we've separated. So second letter cannot be P. And whatever's left over after that. Okay. Now, if the second letter can't be a P, let's identify how many like different letters it could be. Well, it could be O, it could be I, it could be E, or it could be S. So this part right here is there's 4 different possibilities for that spot. Okay. So it's just not allowed to be what P is equal to. So that's just going to be 4. Now, this right here is, well, I've used up one of these letters. So now what I have is I would have 5 remaining elements. So we'll say, and the number of perms for, now we started with 6 elements, 6 letters. Okay, we subtracted 1 because one of them was being used to put to form that second letter. Okay, so we have 5 here. Now, that's what n is going to be equal to. So we're going to have n is equal to 5. Now, just be aware, you still do have a repetition of 2 p's right here. So like we weren't allowed to use one for this first place. That's good, okay? But we still have a repetition of 2 p's. We'll just say a is equal to 2 here. And I know for sure that the 2 p's have to go into this spot because I'm not allowed to use them in that second letter. So we'll have n is equal to 2 for p. Okay, that's enough information now to actually like perform the calculation. So what this would be equal to then is the number of ways I can arrange a single p on its own, which is a 1. Okay, multiply by the number of letters you could put in the second spot that is not a P. Again, we have 1, 2, 3, 4 letters available, okay, from this group right here. And then of the remaining letters, okay, the 2 P's are going to be in there. So of the remaining letters, of which we have 5, so we're going to write down 5 factorial. And then to account for the fact that the p's repeat, we're just going to divide by 2 factorial, multiply these together. We have 1 times 5 1 times 4 times 5 factorial over 2 factorial, and that should be equal to 240. So this is a strategy I would use like if you have like elements with repetitions, and in addition to have elements with repetitions, you also have additional restrictions. Like it tells you this arrangement has to start with this letter or these two letters right here. Okay. Then use this separation technique to kind of like break like the problem into like the one restriction you had to separate and then whatever's left over. So just something a little bit more complicated compared to some of the previous permutation questions we were dealing with. All right, let's go to the next page here. It says we have a class consists of 5 girls and 7 boys. And then we're going to, a committee is going to be formed consisting of 2 girls and 3 boys. Determine the number of ways a teacher can choose the committee if there are no further restrictions to start off with. Usually that word arrangement means we're dealing with a permutation. This one right here, like the order in which they're selected as part of this committee doesn't matter unless like they have defined roles, but it doesn't actually clarify what the roles are. So the idea with this one is that we need to have 2 girls. We need to have 3 boys. So if I want to word this, I can say of the 5 girls, we're going to choose 2 of them. And of the 7 boys, we're going to choose 3 of them. So we can form a simple combination statement. So what this would look like is of the 5 girls, we're going to choose 2. Of the 7 boys, we're going to choose 3 of them. Okay, we can plug it into our calculator. And if we do that, we would get the number of combinations or the number of different ways would be 350. Okay, now B says Johnny, the principal's son, has to be on the committee. Well, first of all, we'll assume he's actually in this class here. Okay. So really what's happening is nothing changes about the girls. Okay. So we still have 5 girls. And we're going to choose 2. And now, if Johnny has to be on the committee, well, that's 1 fewer boy to choose from. So now we're going to say 7 minus 6. 7 minus 1 is 6 boys. We're going to choose well, if Johnny has to be on the committee, then we have 1 fewer spot to fill as well. So instead of like 3 spots, choosing 3 spots for boys for like a boy to fill in, we now have 3 minus 1, which is equal to 2. So again, the whole idea right here is just by clarifying that Johnny has to be on this committee. So that's why we're subtracting 1 here. So like, because he's already on the committee, that's like 1 fewer boy to choose from. And that's 1 fewer spot to fill in. Okay. So that's a result of like Johnny being on the committee, which is like some extreme bias right here, considering how he's the principal's son, but it's just a math problem, although it's kind of absurd if that was actually like a restriction that's required. Okay, so let's form a statement. So this would be 5, choose 2. Okay, so that's for the girls. Yeah, if you want, you can clarify this too, just keep track of things. So this is the girls, this is the boys. Okay, so girls. Okay, boys, so we have 6, and then we're going to choose 2. Multiply these together, and then we're going to have 150. And again, this makes sense compared to the answer in part A, because as you start to place more restrictions in, you're going to have fewer combinations that are available. Okay, C says the twins, Peter and Paul, cannot both be on the committee. Okay. Now, generally speaking, when you see that word cannot, what it's easier to do is it's easier to figure out the number of combinations where they are on the committee and then subtract that from like all of the total combinations. And that's exactly what I'm going to do right here. So we're going to say Peter and Paul not on the committee is equal to all combinations Now, just to point out right here, we don't need to calculate this again because all combinations with no restrictions, aside from the restrictions identified to form the committee in the first place. So this is going to be the same as the answer in A. So we'll just say calculated in A. Okay, and then minus, we're going to find all combinations where Peter and Paul are on the committee. And again, this is usually the way you want to deal with any of these problems that have that word cannot in it, whether it's for a combination or for a permutation. Okay, so let's figure out Peter and Paul on the committee, and then we'll actually calculate this. So let's do this right here. Now, this has no effect, again, on the number of girls that are chosen. So this would still be 5 girls. We're going to choose 2. And, okay, now if Peter and Paul have to be on the committee, well, that means there's 2 fewer boys to choose from. And if they are on the committee, that's 2 fewer spots to fill. So of the 3 spots for boys, we're now going to go 3 minus 2 is equal to 1. Okay, so now we're ready to calculate this. So this would be equal to, okay, all combinations, that's 350. And then we're going to subtract this now. So 5 girls choose 2. So that's going to be 5 choose 2. And then multiply by. And then of the 5 boys that are still available, we're going to pick 1 to fill in to form the total committee. So that's going to be 5 choose 1. So this would be equal to, and by the way, if you're wondering what this is equal to, okay, that's 50. So just the combination of this. So 350 minus 50 would be 300. So again, bit of a tougher question if you have to worry about that word that says cannot. But again, this is generally the way you want to deal with it. Find all combinations and permutations and then subtract, well, if the 2 people are on the committee. All right, one more. Now, this is going to be a problem where we actually have to combine both a permutation and a combination together in terms of doing this like in an efficient manner. So again, this is a bit of a step up in difficulty. Not mathematically, but just logically in terms of how you put it together. So we have this. David, Stephen, and Helen, we're trying to answer the following homework question. Students in a school band have practiced 5 popular and 6 classical music compositions. For the school concert, they will choose a program consisting of 3 popular and 2 classical music compositions. And if the order of the compositions matters, okay, so immediately note right here, it says the order matters, which means we're going to have to do something with permutations. Okay, determine the number of different programs that can be presented. Now, what it does right here is it shows the work for all 3 students. So David says the way to calculate this is 11p5. Stephen says it's 5p3 times 6p2. And then Helen says it's 5 choose 3 times 6 choose 2. Okay, now every one of these answers is wrong, by the way. So we're just going to kind of clarify the logic in terms of like why they are incorrect. And then we'll look at like what the correct way of actually doing this is. Okay, so let's start off with David. Okay, now what he has is he has 11p5. So the idea with this one is what he is saying is there are 11 songs available. And taken. 5 at a time. So going back up here, why is it 11? Well, if you take the 5 popular songs and add it to the 6 classical music songs, that's 11. Okay. And then we're going to choose 3 popular and 2 classical. So add the 3 and 2 together, and that's going to be 5. Now, the problem right here is that his calculation does not distinguish between popular or classical compositions. So this is wrong. Like what he's really doing right here is he's just saying you have 11 songs. We're going to pick 5 of them. What are all the different arrangements that we can get? But again, it doesn't distinguish between those 2 different music genres. So we'll say here, doesn't account for the requirement of 3 popular songs and 2 classical songs. So that's wrong. Okay, let's go down to Stephen's work. So Stephen says the way to calculate this is 5p3 multiplied by 6p2. Now, this one seems more reasonable, but it is also still incorrect, okay? And here's the reasoning why. So what they're saying is of the 5 popular songs, we're going to take 3 of them. Okay, that seems fine because it says we have 5 popular songs. We're going to choose 3 of them. Now, and then what we're going to do, I'm going to really highlight the and then portion right here. You're going to have 6 classical songs. Taken 2 at a time. So the problem with this calculation is what this calculation is assuming is that you were doing all of the popular songs first, and then you're doing all of the classical songs. There's nothing up here that clarifies it has to be like the one genre, then followed by the other one, because you could play the popular song first, you could play 2 classical songs, then you could play a popular one. This calculation tells me directly we're doing 5 popular, we're taking 3 of them, and then 6 classical, and we're taking 2 of them. So the problem with this one is this assumes playing all 3, and we're taking 3 of them, popular, and then 2 classical, in that order. But that was not a restriction identified in the question. If it did say you had to do all of the popular followed by the classical, then that calculation would have been correct, okay? But it's not. Now, Helen. The problem with this one is immediately combinations don't deal with order. So that's immediately where it fails. So we'll say combinations do not account for order. Now, oddly enough, we're going to actually use Helen's work to do the correct calculation in part B here. So Helen's work doesn't care. Like when you find a combination, it's not considering like the amount of order, like what the actual order, the arrangement of these different songs are. So we can use it as a starting point. We can use it as a starting point to identify what all the different combinations are. But then after we calculate all the different combinations, we're just going to figure out, well, what are the different ways you can actually arrange the songs you have chosen? So what's the correct solution to the problem? So I kind of just was explaining it, but I'll just write it down here. So what we're going to do is we're going to take all number of combinations Okay, so that doesn't account for order if we just do it like that. But then after we identify all the combinations and we've chosen our 5 songs, then we're going to figure out the number of arrangements we can have. So then we're going to say, but then account for the order of the 5 songs picked. So we're essentially just starting the combination question. So again, it's important to do a combination to start off with because a combination can actually have like popular followed by classical. Like it doesn't make you have one genre followed by the other one. So it accounts for all combinations, but then we're going to organize the 5 songs we picked. So what this would look like is we'd have 5 choose 3. So that's of the 5 popular songs. We're going to pick 3 of them. Multiply by 6 choose 2. So of the 6 classical songs, we're going to pick 2 of them. Now, what we do then is after we've calculated the number of combinations and I have the 5 songs, then I can figure out the number of different ways we can organize 5 songs. And if you have n elements and you just want to find the number of arrangements for them, you just multiply by n factorial. Okay, so we've picked n is equal to 5 songs, and then we would multiply by 5 factorial. So what we did is we took a combination which didn't account for order, and by multiplying by the 5 factorial, well, then we are accounting for order. So again, it's a bit of a more complicated problem because you have to utilize both a combination equation here or expression, and then to turn it from a combination to accounting for the arrangement, then you have to multiply by the number of different ways you can actually pick the elements you've chosen. Anyway, so if we go ahead and we calculate that, then we would have 18,000 different arrangements. All right, so that's the end of this lesson. The questions you can do to practice this are numbers 2, 4, 6 through 11, 14, 16, and then 18 through 20. And I will talk to you in the next lesson.